Hello friends, welcome back to our video lecture series on course titled Fluid Mechanics 2. In this lecture, we will continue with our topic centrifugal pumps and we will be discussing net positive suction head. Now its name itself indicating that it is a net positive suction head. That means that it is a suction head in terms of a net positive term, and this is what we are going to discuss exactly what is the meaning of the net positive suction head, which is also called as NPSH. Now, whenever we want to take water from this particular water source to the delivery tank, at that time our impeller will start to rotate and there will be a development of negative pressure here, because we know that our liquid always flow from high pressure to low pressure. So if we want to take this water from the sump to the impeller, of course we need to develop a pressure which is less than the pressure at this particular water sump. Now if the pressure at the water sump is atmospheric pressure, then it means that whatever our pressure at the impeller, whatever the pressure at the impeller, which is the suction pressure, so I will write here a suction pressure head. So I will write it as suction head should be less than the atmospheric pressure. Atmospheric pressure, that is P atmospheric. If our this condition is being satisfied, then and then only our flow will take place, because if our pressure at the impeller is not less than the pressure at the water sump, that is atmospheric pressure, then there will be no flow which is being takes place through this suction pipe. So we need to develop that suction head in such a way that it should be less than the atmospheric pressure. Now there is another thing, that if you are reducing your pressure less than the atmospheric pressure, then it may possible that your pressure may go below to the vapor pressure. Now if our pressure is become less than the vapor pressure of that liquid, then of course there would be starting to form vapor bubbles of the liquid inside the impeller, and now those bubbles will collide on the surface of the impeller, and those bubble are going to damage the material of the impeller or maybe the casing, because those bubble is going to continuously collide on the surface, and of course they are containing huge amount of energy which is going to dissipate on the surface of that impeller, either on the vanes or either on the casing, and it is going to damage the material, and this is what the problem of the cavitation. So whatever our suction head which is being developed at the eye of the impeller, that should be greater than the vapor pressure of the liquid. So this pressure should be greater than the vapor pressure of the liquid, and this is what our condition of the net positive suction head. We are going to develop suction head, but in such a way that that suction head should be greater than the vapor pressure of the liquid, because if it fall down the below to the vapor pressure, or if it is become less than the vapor pressure of the liquid, then of course there would be a formation of the vapor bubble which are going to collide on the surface or on the vanes of the impeller or the casing, and those are going to damage those material. So we are going to discuss this NPSH and we are going to derive the expression for it. So let's start. Let us consider this is a centrifugal pump where we need to deliver a water from this water source to this overhead tank, and let us apply a Bernoulli's principle at the eye of the impeller at two sections and at the free surface of the liquid. So let us consider this is our section 1 and this is our section 2. So whatever our P1 upon rho g, that is the pressure at the free surface of the liquid, plus V1 square upon 2g, that is velocity head at the section 1, and Z1 is the elevation of the section 1 from the datum line. P2 upon rho g, pressure head at the section 2. V2 square upon 2g is the velocity head at the section 2. Z2 is the elevation head at the section 2. And HFS, that is the losses which are being takes place in between section 1 and section 2 when my liquid is flowing from this section 1 to section 2. Now if we are considering our free surface liquid as a datum, in that case whatever our Z1 will become 0, because our free surface liquid is our datum and we are measuring our elevation with respect to that datum. So our Z1 will become 0, and whatever this elevation of section 2 from this datum line would become Z2. So this would be our Z2, that Z2 will become equal to HS, that is suction head. Now another thing, whatever the pressure at this section 1 is the atmospheric pressure. So we can write down this as P atmospheric upon rho g. Again, our liquid is static at the section 1. So whatever V1 square upon 2g, value of the V1 square upon 2g will be equal to 0. Now putting those values in our expression of the Bernoulli's principle, what we are getting here, P atmospheric upon rho g, atmospheric pressure at section 1 plus velocity head, and the section 1 is 0 because here velocity is 0, our liquid is static. As we are considering our free surface liquid as a datum, so our Z1 is also 0. P2 upon rho g, pressure head at the section 2, that the at the eye of the impeller. V2 square upon 2g, that is our velocity head inside the suction pipe, so that I am replacing it with the Vs square upon 2g, that is velocity in the suction pipe. Hs, that is Z2, as we are considering this as a datum, so this would Hs will become our Z2, and losses, head loss, which is going to take place through this suction pipe. So if I want to compute whatever the pressure I required at this eye of the impeller, so I need to find here P2 upon rho g. So if I write down this expression in the form of P, where my liquid is flowing from section 1 to section 2, then whatever my P2 will be equal to P atmospheric. I'm taking this all expression on this side, what we are getting, P atmospheric upon rho g minus, in bracket, V square upon 2g plus Hs plus Hfs. Now this expression indicating that whatever your pressure at the eye of the impeller should be less than the pressure at the free surface of the liquid or at the water sum, that is less than the atmospheric pressure, because if you see here, something is going to deduct from our atmospheric pressure, and it is that term which is going to deduct from the atmospheric pressure, that is V square upon 2g plus Hs plus Hfs. This term is going to be subtracted from this expression P atmospheric upon rho g. That means that our P2 upon rho g, value of P2 upon rho g should be less than atmospheric pressure or whatever the pressure head available at the water sum. Then and then our flow will be takes place from the section 1 or section 2, otherwise it will not. Now this equation, it is giving us the total suction head that should be developed at this particular impeller, and which should be the less than the atmospheric pressure. Now for avoiding cavitation, whatever this value of P2 upon rho g should be greater than whatever our vapor pressure, value of the vapor pressure, PV upon rho g. Then and then our cavitation will be avoided, otherwise vapor bubbles will start to generate in this particular section, and due to that, of course, our material may get damaged due to the formation of the cavitation. So for the avoiding cavitation, this P2 upon rho g should be greater than PV upon rho g. So in simple words, I can say that this P2 upon rho g is equal to atmospheric pressure minus the value of velocity head plus suction head plus Hf, and minus vapor pressure of the liquid, that is PV upon rho g. And now this term should be a positive. The value of this P2 upon rho g after deducting this vapor pressure should be positive. It should be positive. If it is coming negative, that means that whatever your pressure at section 2, that is at the eye of the impeller or the suction head, is less than the vapor pressure, and due to that there may be a formation of the bubbles, and due to that bubble our material may get damage. So for avoiding that, the value of this P2 upon rho g should be positive after deducting this vapor pressure from this given expression. So I can write down that expression as in this form, and the value of this expression, that is this value of this P2 upon rho g should be positive, and this is called net positive suction head. Or in other words, I can simply say that P2 upon rho g should be greater than PV upon rho g. And if I take it on the LHS, what I am getting here, P2 upon rho g minus PV upon rho g should be greater than 0. That means that it should be positive, and if it is positive, we can avoid the cavitation, and value of this P2 will be given by this expression, and this P2 will be of course less than the atmospheric pressure, but it should be greater than this PV upon rho g. Sometimes the expression of this NPSH is written in the form of, let's say, P2 upon rho g minus PV upon rho g, that is vapor pressure, plus velocity head at the impeller, because whenever my water is coming through this pipe, at that time it will have a certain velocity at the eye of the impeller that should be get added. So whatever the NPSH we are calculating by using this expression is known as available net positive suction head, which is also written as NPSH. And this NPSH should always be greater than NPSH required. Generally, this required NPSH is being provided by the manufacturer. So whatever our available NPSH should always be greater than the required NPSH. Now, this is the expression by which you can calculate net positive suction head, which is given by the P2 upon rho g minus PV upon rho g plus Vs square upon 2g, where this P2 is the pressure at the impeller and PV is the vapor pressure of the liquid and Vs is the velocity of the fluid, the suction pipe. Remember that whenever we are talking about the expression, this expression P2 upon rho g is equal to P upon rho g atmospheric minus Vs square upon 2g plus HS plus HFS minus P upon rho g vapor pressure head. So the value of this particular equation should be positive. That means that it should always be greater than 0, and this term is known as net positive suction head. So we are developing suction head, but in such a way that if you are comparing it with the vapor pressure, then its value should be positive. So if you are deducting the vapor pressure from our suction head or suction pressure which is being developed at the eye of the impeller, then this value should be positive, and then we can ensure that there will be no formation of the bubble inside the impeller. So hope you understood this concept of the net positive suction head. Those are the references which I have used while preparing my presentation. Thank you for watching.